Alright, thanks for watching, and today we're gonna solve the hottest equation of them all, namely the heat equation, or sometimes called diffusion equation, which in general is just given by ut minus Laplacian of u equals to 0. Or if you want in one dimension, it's just ut minus uxx equals to 0. And this equation is actually very important because Fourier actually studied this equation to find Fourier series. Really, really cool, but today we're gonna try to find solutions directly, and it'll lead to an interesting observation. So, the interesting thing here is this equation actually behaves sort of like Laplace's equation, and actually not really, but what I mean is that to find the solutions of this equation, we'll tackle this like we did for Laplace's equation. Namely, we're going to look for solutions of a particular form and then figure it out what the solution is. And let me just give some little motivation, because I'll write down a little formula soon, but I want to motivate this formula. So, for Laplace's equation, we assume that the function u is radial. So we said u of x is v of absolute value of x. So a function that just depends on the radius. And how did we figure this out? Well, again, here's a silly motivation, but Laplace's equation, right? It's x1 plus etc. plus xn equals to 0. And if you replace those ones by square, like x1 squared plus plus xn squared, again, very non-rigorously, you might think, oh, well, the solutions should just depend on this factor, which is the length of x squared. And that's where we guess u of x to be v of length of x, or length of x squared. That's completely fine. And here we want to do something similar. Again, it's a silly motivation, but ut minus Laplacian of u equals to 0. That's the same thing as saying ut minus ux1 etc. minus uxn equals to 0. So, similar to before, maybe the following term enters in: t minus x1 squared minus xn squared equals to 0. And if you write this down, if you work this out, basically you get t minus absolute value of x squared equals to 0. And this gives you t equals to length of x squared. So length of x is, since it's positive, it's square root of t, which gives us x over square root of t equals to 1. So maybe, again, just as a motivation, our solutions will involve the term square root of x over t. And in fact, we're going to do something like that. So, as I said, our approach is simply to look for solutions of a particular form. So here, it might be good to guess u of xt equals to some function of this new term, which I believe it's called the symbol of the operator. So it's not entirely gibberish, it actually is motivated by something. So our guess is maybe in this case, guess that u is a function of absolute value of x divided by square root of t for some v. And in fact, you could do this and it would work. It's just it would take 3 times as long. And just to speed up the process, and because it is correct, let me tweak this a little bit. So, first of all, instead of saying absolute value of x divided by t, suppose v is a function of x over square root of t. So v goes from Rn to R. And here I guess v is Vy. And moreover, again, that comes later, we assume that v is radial. V is radial, just like for Laplace's equation. In other words, v equals to some other function of the absolute value of y. Again, this we'll need later. And moreover, it turns out solutions to the heat equation become a little bit singular. So what I'm going to do, I'm also going to pre-multiply this by a factor of 1 over t to the n over 2. Okay. And by the way, I chose those constants already, but if you want to, it's like find the Easter egg if you want. If you want to do this in full generality, you would start by saying 1 over t of alpha, v of x over t of beta. Plug this into the PDE and then find alpha and beta. But let me already give them to you and I'll tell you exactly where they're very important and how you would in general guess for alpha and beta. All right. So this is our new guess. We're going to guess that u is 1 over t to the n over 2 v of x over absolute value over square root of t. And now essentially what we're going to do is find v. So for the next 30 minutes or so, our quest is to find this function. And then we get a solution of the heat equation. Okay, well now that was sort of step 0, the motivation. Let's do step 1. So plug this guess, or Ansatz, one of my favorite words, plug it into the PDE. Into ut equals to Laplacian of u. So let's do this. So t to the n over 2 minus n over 2 v of x over square root of t. T equals to Laplacian. Again, with respect to the x variables, so our Laplacian of x, t to the minus n over 2 v of x over square root of t. Okay, and I guess let's roll up our sleeves and differentiate this, but fortunately my sleeves are already rolled up. So, we want to use a product rule. So minus n over 2, t to the minus n over 2 minus 1. And again, in this case, let's just leave it as v of y. Or I'd like to remind you, y is just x over square root of t. And then plus, so t to the minus n over 2, v of x over square root of t, t. And again, I will calculate this in a second, but for the Laplacian term, it's actually much easier because this is constant with respect to x. So this comes out. And basically, what is Laplacian? It's just, x1 plus dot 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 plus, I guess, Laplacian of u is ux1 plus dot 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 plus uxn. So basically, if you differentiate this once, let's say with respect to x1, you have a factor of 1 over square root of t that comes out. If you do it twice, you get 2 factors of 1 over square root of t that pop out. So basically, you get 1 over square root of t, 1 over square root of t, and the Laplacian with respect to the variables of v, which is just Laplacian y of v, of y. We're almost well, almost done with this part. Let's just do the t derivatives, just for sake of completeness. Alright, so let's see, v of x over square root of t. T, really in terms of variables, that's v of x1 over square root of t, dot 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 xn over square root of t with respect to t. And now just use the chain rule. So that's really vy1 and the derivative of that with respect to t, which is, I think, minus x1 over 2 t squared of t. Again, just use the power rule, plus dot dot dot, plus vyn minus xn over t squared of t. Right, and the reason I'm doing this, we can write this in a nicer form. And notice, so everything here basically depends on y, and so we just want to write this in terms of y. And again, I like to remind you that y is x over square root of t, and so that's x1 over square root of t, dot 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 xn over square root of t. So this is almost x over square root of t, except with this little factor of t here. That should be a 2 here. And so if you factor out, if you want, minus 1 over 2t, that's vy1 x1 over square root of t, plus, so here it's multiplication, vyn xn over square root of t. And this then becomes, so minus 1 over 2t. If you want, the vector of all partial derivatives of y, so of v, so dyv, dotted with y. There's a reason I'm doing that, because now we can rewrite this equation. So turns out this term simplifies pretty nicely, and in the end what we have is minus n over 2, t to the minus n over 2 minus 1v, plus t to the minus n over 2, again times, if you want, minus 1 over 2t dvy dotted with y. And here you also have t to the minus n over 2 minus 1 Laplacian of v. And we're almost there at the simplification part, because the t's are pretty annoying. It would be nice if they disappeared, but let's see. Minus n over 2 t to the minus n over 2 minus 1v plus, I guess, minus 1/2 t to the minus n over 2, but because of this minus, we have a minus 1, dyv dotted with y, and t to the minus n over 2 minus 1, Laplacian of v, and lo and behold, all the t's here disappear. Math is beautiful. All right, and you might say, wow, this was magical, but why did that work? It's basically because we guessed, again, remember for a guess of u was 1 over t to the n over 2, v of x over square root of t. Surprisingly, this cancellation has nothing to do with this factor. It has to do with the fact that we chose square root of t. So basically, if you wanted to do it in general with v of x over t to the beta, I guess 1 over t to the alpha, you would do the calculation and then choose beta to be 1/2 to actually make all the bad terms disappear. Okay. So we took this complicated equation and turned it to maybe something easier. We'll see. So now we are left with the following equation. Step 2. And I'm sorry, I may have miswrote it before, but we're left with n over 2v so that's from the cancellation, plus 1/2 dv dotted with y equals to, if you want minus Laplacian of v, but you put it on the left hand side, so plus Laplacian of v equals to 0. And this is sort of good and bad news. The good news is there's no more t. So essentially we reduced it to a PDE in one less variable. And like the song goes, I got one less variable without you, I got one less variable without you, or something like that. So a PDE in one less variable, but in my opinion this is more complicated than the heat equation. So we had a trade-off in some sense. Still, this is very good, and let me give you an analogy. This is like in multivariable calculus, where you started out with a double integral and turned it into a complicated single integral. Even though it's more complicated, it's still a single integral. So that's good. And in fact, in this step, what we're gonna do, we're gonna turn this into an ODE. So make it even easier. And for this, we have to use the fact that v is radial. So recall, right, v is radial. That means v of y is some function of the length of y, and length of y, let's just call it r, and for some function w going from r plus to r. For example, just to illustrate, let's say you had the function 1 over x squared plus y squared, that is 1 over r, so if you want v of r is 1 over r. Okay. Alright, and now what we want to do, we want to plug in this expression, this ansatz, into the PDE, but it turns out I've actually done most of the work in another video about Laplace's equation. So let me recall also the following. It turns out that if v is a function of the radius, it's actually very easy to calculate the derivatives. Namely, if you use the chain loop, the derivative of v is w prime times the derivative of absolute value, which is y over absolute value of y. So dv is w prime y over length of y. And moreover, the Laplacian, you can also calculate it. Laplacian of v just becomes w double prime plus n minus 1 over r w prime, where prime is d over dr. This is sometimes called the radial part of the Laplacian. All right, wonderful. So we have this. Let's not plug this into the PDE. So we're left with n over 2. Remember, v is just w, but in those radial coordinates. So w plus 1/2 dv, which is w prime y over length of y dotted with y, and Laplacian of v is w double prime plus n minus 1 over r w prime, and all this junk equals to 0. And it turns out we can eliminate this y, because y dot y is just length of y squared. You're dividing this with the length of y, so you're left with length of y, which is r. And so in the end, you have n over 2w plus 1/2 w prime r plus w double prime plus n minus 1 over 2 over r, w prime. 0. And if you'd like, how about we just factor out, a factor of 1/2. So 1/2 of w prime r, and I'll explain why we knew that. Okay. 1/2 w prime r plus n over 2 plus nw for the win, or for the wn, plus w double prime of 1 plus n minus 1 over r w prime equals to 0. And this is very, very good. We took our, first of all, we had the heat equation, which was a PDE in several variables. We turned it into a PDE in one less variable, and in fact, that PDE, we just turned it into an ODE. So all that's left to do is to solve that ODE, and it turns out we can do this. All right. And the question is, how can we solve this ODE? Slightly trickier, but there's a reason I wrote this in this way. Because notice, this sort of looks like the product rule. Because we're differentiating W and we're leaving R intact. And then we're not differentiating W and sort of differentiating R, except with this extra factor. And same thing here, we're differentiating W and not doing anything here. And then we're not differentiating W prime and with this other factor. And it turns out we will be able to turn this into the product rule. Namely, so I guess this is step 3. Take this ODE and multiply it by what's called an integrating factor. In this case, multiply by Rn minus 1. Then, what you get is 1/2 W prime R times R to the n minus 1, which is R to the n, plus W n times R to the n minus 1, plus W double prime R to the n minus 1, plus, if you want, W prime n minus 1, R to the n minus 1 over R, which is R to the n minus 2, equals to 0. And that's wonderful. That's precisely the product rule. Namely, we get W prime times R to the n plus W times the derivative of R to the n. So 1/2 R to the n W prime. And here it's the same thing, but with W prime. So we differentiate W prime. You don't differentiate R to the n minus 1. Then you don't differentiate W prime, and you differentiate R to the n minus 1. So we have this equals to 0. And notice there are a bunch of miracles happening, really. And in fact, we get this prime plus this prime, so we're left with 1/2 R to the n W plus W prime R to the n minus 1 prime equals to 0. Alright, and by the way, so I said it's a miracle. Not really. This part works precisely because we chose the factor, I think, t to the n over 2 in this. Remember, we had v of u of x over square root of t. So in general, you would again do it 1 over t to the alpha, v of x over t to the beta. Do all your calculations, and then choose alpha equals to n over 2 and make this problem work. Alright, but anyway, that's great. We have this ODE, we can solve it. So we get 1/2 R to the n W plus W prime R to the n minus 1 equals to a constant. And now I'd like to remind you of something. We're not trying to find all the solutions of the heat equation. We're just trying to find one solution of the heat equation. Just like we did for Laplace's equation. We just wanted to find one of them. And in fact, just to find one solution, let's just set this constant equal to 0. Again, we just want 1. If we have 1, then we can go home happy. And so, we're then left with so interesting, honestly, because we have this, again, we had the complicated PDE, right, in x and t. We turned it into a PDE in x. We turned that into a second order ODE. Now, in fact, we turned that into a first order ODE. So, it shows that each step it becomes simpler and simpler. So, what do we have? 1/2 r to the n w plus w prime r to the n minus 1. We remember we set that equal to 0. And so now w prime r to the n minus 1 equals to minus 1/2 r to the n w. Assume our function is positive, again, just heuristically. W prime over w. So we divide this by w, we divide the other side by r to the n minus 1. So r to the n over r to the n minus 1. And so this becomes ln of w prime equals to, so this chunk becomes minus 1/2 r, because this is one factor bigger than that, so minus 1/2 r. And now we can anti-differentiate this, so ln of w is minus r squared over 2, over 4, sorry. So r squared over 2 times minus 1/2 is minus r squared over 4 plus some constant. And this constant turns out is important, so let's not eliminate that quite yet. Because if you choose it to be 0, I believe, well, no, w wouldn't be 0, but again, trust me, there's a reason why this is important. So then you just exponentiate. So w becomes e to the minus r squared over 4, e to the c. This, again, c is a generic constant, so let's call, well, getting ahead of myself. So w is plus or minus e to the c, e to the minus r squared over 4. Now, plus or minus e to the c, because c was a generic constant, let's just relabel this as c. And so, do you see what is happening now? We find w of r, c e to the minus r squared over 4. And now we have to go back to v and then to u. So that's step 5. Our conclusion, so w was this. Then remember what v was? V was just, the non-radial part, if you want, of w. So w of absolute value of y, which becomes here c to the minus absolute value of y over 4. And last but not least, u of xt becomes our constants, right? 1 over t to the n over 2, v of x over square root of t. And that becomes, if you want, 1 over t to the n over 2, c e to the minus x over square root of t2 over 4. And last but not least, we have our solution. U of xt is constant over t to the n over 2, e to the minus, so this becomes x squared. Square root of t squared is t, so in the end we get 4t. And lastly, to make a function that has integral 1, what we're going to do, just choose a special value of the constant. So again, you could just set c equals to 1. It's fine. It would give you a solution. But to have an interesting solution, choose c is 1 over pi to the n over 2. Just in tribute of pi n, right? And we're left with u of xt becomes, again, 1 over pi to the n over 2 t to the n over 2. So 1 over pi t. Sorry, I meant to say the following constant, 4 pi. Alright, this is great. This gives us a solution. In fact, infinitely many solutions of the heat equation. But turns out there's one that's extra special, namely that has integral 1, namely simply by choosing c equals to, let me see, 1 over 4 pi to the n over 2. Just in tribute of pi and n, okay? It's almost pi n, so close. And in the end, you get u of xt to be 1 over 4 pi to the n over 2 times t to the n over 2, and that's the same thing as 1 over 4 pi t to the n over 2, e to the minus x squared over 4t. And this function is so important, it has a very nice name, it's what's called the heat kernel. Because just like for Poisson's equation, where you can write this in terms of the fundamental solution of the heat equation, of the Laplace's equation, this heat kernel also comes up in the solution, I guess, of the inhomogeneous heat equation, and also the heat equation with the initial condition, because I haven't done that at all. And if you want, it sort of looks like the normal distribution. It starts out like the normal distribution, and then because of this smoothing factor, it goes like down and down. And so interestingly, this has a singularity at t equals to 0, but this singularity completely disappears as t is positive. So unlike Laplace's equation, this singularity doesn't give us much trouble. Alright, so I hope you like this excursion into the heat equation. If you want to see more PDEs and more math, please make sure to subscribe to my channel. Thank you very much.